Here in this quiz, we're going to be looking at light and how to get energies from wavelengths and other properties of light and the Bohr model of the atom. And remember that the Bohr model, while not a perfect model, still does explain the hydrogen emission spectrum pretty well, which is an experimental result that we need to be able to describe by any atomic model that we use. And therefore, the Bohr model is really the first one that we look at and is foundational to our modern understanding of the atom. So how does light interact with it? First, we're going to see how individual photons of light can be calculated in terms of their energy based on the wavelength of that light. And so in the first question, we're trying to calculate the energy associated with the purple or violet band in the hydrogen emission spectrum. That has a wavelength of 410 nanometers. And we have a couple of wave equations that we've been given up top. The first thing we need to do here is we need to get the frequency. So this is equation 2 that tells us that the speed of light is equal to the frequency of light multiplied by its wavelength. We know the wavelength and the speed of light already, so therefore we can calculate that the frequency is equal to 7.32 times 10 to the 14 per second, or hertz is a common unit that we can see as well. It's equivalent to per second, which is seconds to the -1, or 1 over second, right? It's kind of like meters per second, but without the meters, right? Per second. And this is if you were to watch the light come at you, you would see 7.32 times 10 to the 14 crests hit your eye every second. And that makes sense because light is moving really fast and the wavelength is really short. Okay, so we have the frequency for light. What do we do to get the energy? Well, this is where we want to use equation 1. And remember that while equation 2 is generalizable to pretty much any type of wave, equation 1 is really just for photons of light, right? It's a constant that relates the frequency of a photon to its energy. And so we use that equation, we plug in Planck's constant, and we end up with units of joules. Frequency is units of per second, 1 over second. Planck's constant is in terms of joule seconds, so joules times seconds. So joules times seconds divided by seconds gives us joules. That's an energy unit that we should like. And we see that it's a pretty small amount of energy, which is because this is a pretty small amount of light. It's a particle of light that interacts with an electron. So this is how we calculate the energy of a single photon. If we want to do so for part B here for a red wavelength, it's really the same process. We're just using a different frequency and a different wavelength, because it has defined a different wavelength. And so we get the frequency for the red light, which we note is a little smaller than the frequency for the violet. Violet has a shorter wavelength, therefore a larger frequency. Red has a longer wavelength, therefore a smaller frequency. And we get the energy for the photon, and we see that the red has slightly less energy. Now, I think that it is tempting for students here to combine equations 1 and 2 to say, a single equation that expresses the energy in terms of the wavelength. But I honestly don't think that saves you any time, really. I mean, I think you still have to do the same amount of algebra. And while you may only have to remember one equation, it does miss out on the fact that equation 2 is more generalizable than equation 1. And therefore, by combining the equations, you miss out on that nuance and that opportunity to appreciate what both of these fundamental equations represent. I really think that they're best remembered as a pair and not trying to combine. Okay, the next question is saying, well, based on the answers to A and B, which represents a larger transition for the electron within the hydrogen atom? And this requires that we understand what these are within the Bohr model, right? Each of these specific energies represents the energy it takes to promote an electron from one energy level to another. And we don't know what energy level it's bouncing from and to just based on the context of this problem. I mean, it's well studied, so it is known. But we don't really need to. What we do want to understand is that the larger the energy, the larger the transition. The energy of the photon corresponds to the energy of the transition. And so if we think about our different wavelengths of light, this is the full spectrum. It goes all the way from radio on the right to gamma rays, cosmic rays, and really high energy rays on the left. And in the middle, there's just a small band of visible light for which we have red as the lowest energy and violet as the highest energy. All we really need to know here is that the violet photon has more energy, therefore it's going to correspond to a higher energy level transition. The violet is going to make an electron gain more energy than the red does, Therefore, it's going to correspond to a larger transition of energy within the hydrogen atom. Final question here is to say, well, what if we do know what the transition is and that the violet band is from the 6th energy level to the 2nd energy level, right? If an electron should be at energy level 6 and drop to energy level 2, it's going to emit this specific violet photon. We want to know how the energy compares for a photon that should be emitted if that electron fell not from 6 to 2, but from 6 to 1. And we want to just estimate the color or type of radiation associated with it. And so, estimate here, there's a lot of possible answers. If we don't know more, that's fine. We're not going to be able to nail down an absolute specific wavelength for this transition without more information. But it is really good to be able to have a ballpark, know what direction the transition is being pushed in. And so what we do know for sure is that if the transition is from 6 to 1 as opposed to 6 to 2, that it's going to be more energy. And therefore, the photon needs to represent one of greater energy. N equals 6 to N equals 1 is a larger transition than from 6 to 2. Therefore, the energy gap is larger. Therefore, the photon must have more energy. And so all we can really say here is that it's going to either be violet of a shorter wavelength or ultraviolet or even higher, right? A good answer is pretty much anything to the left of violet on this chart. And it turns out that it actually is an ultraviolet spectrum. If you're looking at your textbook and looking at the transition series that goes to N equals 1, they're all in the UV range, and so that would be where this answer actually lies. But if you said gamma ray for this one, or X-ray, or violet, all of that would be okay, and what would not be okay would be blue, green, red, infrared, or anything to the right. We know it's not going to be those because those have less energy than the violet photon that we already know corresponds to N equals 6 to N equals 2.